I tell you what, I don't know why I have so much trouble with my audio visual stuff. But we're going to try to muddle through somehow. Lord, I ask you to help, please. I've had so much technical troubles the last 2 weeks. So please let me get through this without any of that stuff. We want to honor you and glorify you, Lord. That's what all of this is all about. So just receive glory through everything that we do and say tonight in Jesus' name. Okay, last time we talked about astronomy, and that's really a lead into physics. So I want to talk about physics. Classical physics is distinguished from modern physics. Classical physics has to do with things like, visible phenomena. Relativity is part of modern physics. That has to do with time dilation, with extreme gravity, things like that. Well, that's not what I'm mainly going to focus on. It's mainly going to be the study of forces, motion, energy, waves, optics, acoustics, things like that that are capable of investigation without having high-powered equipment like a particle accelerator or something like that. Things you can do with ordinary instruments. So it's often called Newtonian physics after Isaac Newton. Newton was a devout Christian, and he actually wrote more on the subject of religion and the Bible than he did on the subject of physics. A few years ago, I went to the American Association of Physics Teachers Conference up in Salt Lake City, and we had 3 Nobel Prize winners speak to us. One of them, Dr. Horst Sturmer, kept going through his speech, and he was saying that Mother Nature did this, Mother Nature did that, Mother Nature did the other thing. Well, at the end, he hung around in case anybody wanted to go shake his hand. I said, "Ooh, cool, shake hands with a Nobel Prize winner? That's neat." So I got in line, but I deliberately got to be last in line because I wanted to have a chance to talk to him. And when I finally got up to him, I said, "Dr. Sturmer, don't you think that a reasonable person could conclude that instead of Mother Nature, there could be a Father God?" He said, "Well, I'm a scientist." I said, "Okay, but so was Isaac Newton." "Yes, but that was centuries ago." Isaac Newton was one of the most brilliant men of all times, and he's widely considered to be the greatest scientist of all times. Einstein was great for theory, but he didn't do any practical stuff. Newton did both theory and practical stuff. So he was really a great scientist, and it pretty much bothered me that this guy would say that we progressed beyond that point. And I realized as I walked away from shaking hands with him, he's a professor, I realized this is who the Bible's talking about, professing themselves to be wise, they became fools. Because he's exchanging the glory of God for the glory of Mother Nature. It's really sad that somebody would do that. Okay, so Isaac Newton, he recognized that he owed much of his success to the people that had come before him. He once wrote to a friend of his, "If I see farther than others, it is because I'm standing on the shoulders of giants." Let me tilt this down a little bit. What he meant was that there had been people before him like Galileo, Copernicus, some of the guys that we talked about last week, and he was a contemporary of another guy named Leibniz who was working on developing calculus at the same time as him. So Newton recognized it wasn't just that he was such a genius, it's that he read the works of other people before him. And I was emphasizing this today. I was substituting in a biology class, going back over the scientific method with him, and I told him, if you don't do research into what's been done before, you're stupid, because you're probably wasting an awful lot of time. So Newton recognized that he owed a great deal to his predecessors, and he was a devout Christian throughout his life. Now, an interesting thing that happened to Newton, he began his training in 1661 at Trinity College in Cambridge, near London. And, you know, Cambridge, whoa, that's one of the world's foremost universities. Well, while he was there doing his studies, it was just outside of London the bubonic plague began to spread outward from London. So Newton moved to his family's estate, which was about 60 miles away, and he stayed there until the bubonic plague died down. That's a whole lot worse than COVID. And so while he was there, he continued his studies, and it wasn't that all of a sudden he got these ideas. He just continued and developed these ideas which he'd been working on before. He discovered while he was there the law of gravity and his three laws of motion. When I say you discover the law of gravity, well, gravity is there for everybody, but the law of gravity is the mathematical description of how it works. And he worked it out mathematically while he was there. He's also credited with inventing differential calculus, and he studied light, colors, vision, optics, many other topics too. So he's just like one of my really cool heroes. But have you ever heard the idea that an apple fell on Newton's head and that gave him the idea for the law of gravity? No, it didn't actually fall on his head. Newton himself wrote that he was sitting on the bench in the garden and an apple fell in front of him. And he realized that thing fell toward the center of the earth, but if it fell in India, it would have also fallen toward the center of the earth. And the moon is going around and it's continually being pulled toward the center of the earth. What force is that? So he realized, okay, there's gravity, and he worked out the details for how gravitational attraction works. So the starting point is energy. I gave a talk one time at the Pontchartrain Astronomy Society, and these guys believe in the Big Bang. They believe in pretty much atheistic evolution. And when I went out there, I said, I appreciate the fact that nobody brought torches and pitchforks, and they laughed about that, you know, because I'm a creationist. And Dr. Sieb, Greg Sieb, who was the chairman of the physics department at the time, and he said I was his favorite creationist. I took a class with him in astronomy. But at the end of my talk, which was entitled, What Do We Know for Sure About the Universe? And the answer was not a whole lot. At the end of my talk, somebody said, well, what's energy? And I told them, if I could give you a definition of energy, I would win the Nobel Prize. We don't know what it is. And Dr. Sieb said, yeah, I'd vote to give it to you too. But I'll tell you how I am like energy. Nancy knows this already. Energy is the ability to do work, but work is the amount of energy you put into something. That's a circular definition. I prefer to think instead of energy is the ability to produce change. So how am I like energy? I just produced a bunch of change out of my pocket. So I'm like energy. So there's two major types of energy. One of them is called kinetic energy, which has to do with motion, and the other one is called potential energy. That's the energy that has to do with position. So for instance, if an object is some distance above the Earth's surface, it has gravitational potential energy. If two magnets are held at a certain distance apart, they may be trying to pull together or push apart. They have magnetic potential energy. If a spring is stretched, it has elastic potential energy. You can put two electrically charged objects close by and they'll have electric potential energy, and there's also chemical potential energy, nuclear potential energy, a great many things like that. Okay, so I want to, before I get to anything else, talk about thermodynamics. Thermo sounds like heat, right? Well, yeah. Thermodynamics implies heat, but energy can change back and forth from one form to another, and so everything eventually tries to turn into heat anyway. So all energy usage is thermodynamics. There are two laws of thermodynamics that have been discovered and confirmed through century after century after century. And remember, a law doesn't make anything happen. And I can't get this thing straight. Oh well. For those watching online, sorry. A law doesn't make anything happen. A law just describes this is what happens. And then if you're trying to figure out why something happens, that's where you bring a theory in. But the first law of thermodynamics and the second law of thermodynamics have been tested and tested and tested for centuries, and there's never been a single exception observed. So if somebody would come up with an exception, they worked so well, we would probably say, well, let's modify it a little bit. But so far, we haven't had to do any modifications at all to these laws. The first law of thermodynamics has to do with the quantity of energy. It says that energy can be neither created nor destroyed by any known process. So, to put it another way, the total amount of energy in a system that's not subject to outside influence, like the whole universe, the total amount of energy is constant. You can't increase it. You can change it back and forth from one form to another, but the total amount is constant. You can change heat to light, light to electricity, and we have the equation from Einstein, E = mc squared. That is, you can convert matter into energy, and the quantity of energy you get is described by that equation. That's all it is, very simple equation. So very closely related to that is something called the law of charge conservation, which says if you have positive and negative charges in a system, the total remains constant. That particularly applies to chemistry. Okay, and then this one is called the second law of thermodynamics. It has to do with the quality of energy. There's an expression or a term called entropy that describes the randomness or disorganization of a system. And what scientists have discovered over centuries is that unless forced to do otherwise by an outside influence, energy tends to flow from a greater to a lesser concentration. So, for instance, unless some external influence makes them do otherwise, if you put a hot object and a cold object touching each other, is the cold object going to get hotter? No, the heat is going to flow from the hotter one to the cooler one. Energy tends to flow from greater concentration to lesser concentration. Now, you can, by deliberate action, make it go the other way for a while. That's what happens in living things. Your DNA enables your body to put together stuff in opposition to the second law of thermodynamics. If you didn't have any DNA, that wouldn't happen. Everything would just continually flow apart. So electric charges tend to spread out from a battery rather than assembling themselves together in it, and energy tends to spread out from a star rather than coming back together into the star. And when a bomb explodes, the energy spreads out rather than pulling itself back together. That doesn't mean there could never be an instance where energy spontaneously became more concentrated in a local area for a very short time. This is a general principle. Overall, there's a trend toward deterioration, toward equilibrium of the universe. You could have a very temporary local reversal, but then it's eventually going to go the other way. Thermodynamics wins in the end. So think about this. What would cause, if there was a Big Bang, which most people believe there was, if there was a Big Bang, and I don't, by the way, later on the stars formed, what would force the energy that's expanding? It would be a cloud of gas and dust expanding outward from a Big Bang. What would force that to come together and form a star here, and a star here, and a star here, and a star here? Trillions of times. It's estimated there's at least about 10 to the 23rd power stars in the universe. So every time a star came together, the second law of thermodynamics would have to be overridden by something. Well, if you have a specific force, you can override it, but what force would that be? And in chemistry, they're estimated to be about 10 to the 80th power atoms in the universe. But if you've got this energy spreading out, why would it say, oh, let me come back together there and form an atom, let me come back together there and form an atom? 10 to the 80th power times. Why? What mechanism would cause that to happen? Now, those that believe in evolution say, I just did. There's an expression called hand waving. When you don't have a good argument, you say, it just did. You just wave your hand. Well, this is all hand waving. I believe in one process whereby a supernatural being, God, an incredibly intelligent and powerful being, did all of this stuff. I don't know how he did it, but I believe that one time he overrode the laws of nature, or he hadn't even set them into effect yet. If you believe in evolution, you have to believe at least 10 to the 80th power times that random chance processes overrode the second law of thermodynamics for the atoms, and at least about 10 to the 23rd times for the stars. You can't prove that. I can't prove there's a God. I just think it's much more reasonable to believe that there was one unexplainable event as opposed to 10 to the 80th power unexplainable events. And in biology, what would force energy to concentrate it? It's trying to spread out, but it's going to concentrate itself first in the early Earth's oceans. The chemicals come together to form amino acids, and then the amino acids come together to form proteins, and also nucleic acids are coming together. What would make that happen? There would have to be some kind of an outside influence, but if you don't want to believe in God, you'd have to say there is no outside influence. So let's talk about how objects move. Are you moving? Well, looks to me like, those that are here, looks to me like you're sitting still. So my question, are you moving? If there was an observer in a spaceship looking down at you, you'd say, man, look how fast they're moving. From your perspective in the chair, you're not moving. From that person's perspective in space, you are moving. So if I ask, are you moving, you need to respond with a question. Compared to what? Compared to a beach chair sitting on the equator, you're going 0 miles an hour, you're just sitting there. But if you compare that to the moon, here's the moon as a frame of reference out here. The beach chair is going around with the Earth's surface, the equator, and the beach chair is moving over 1,000 miles an hour, about 1,040 miles an hour. But you don't feel it. And then compared to the sun, here's the sun in the middle, and the Earth is going around at about 66,000 miles an hour. And I believe I mentioned this last time, the sun is dragging the whole solar system along with it at about 1,000,000 miles an hour. So are you moving? Compared to what? You always have to have a frame of reference. There's many different frames of reference can be valid for analyzing motion. Like if you're watching a race, you could measure from the starting line, from the finish line, from somewhere down the middle. Any one of them is valid. You just need to make sure that you're consistent when you're working out the mathematics. Now there's also many measurements that involve not just an amount but a direction. So these become important when you're talking about inertial and non-inertial frames of reference. An inertial frame of reference is what you can use to do very simple measurements of motion. It's a frame of reference that's not accelerating. So right now, are you accelerating? Well, we don't think we are. If you're in an airplane, when you're taking off, you definitely feel the acceleration. But once you're up there at 550 miles an hour and it's nice, smooth skies, you're moving at 550 miles an hour. Are you accelerating anymore? Well, not that you can feel. Your inner ears can detect a certain amount of acceleration. And acceleration is either a change of speed or direction or both. Well, suppose you're sitting in the beach chair on the equator and you're just relaxing and chilling. Would you be accelerating? You're going at 1,000 miles an hour, but acceleration is also a change of direction. So right now you're going that way. In 6 hours you're going that way. 12 hours you're going that way. 18 hours you're going that way. 24 hours you're back that way. You've changed directions all the way around a circle. It's just your inner ears are not sensitive enough to detect it. But you are accelerating. But in general, we approximate the Earth as being an inertial frame of reference because we can't detect the acceleration. But there is a device that we'll probably get to later on called the Foucault pendulum that can actually detect the rotation of the Earth. It's a long thing. It's like 60 feet long, and it swings back and forth, and the Earth turns under it. So that's an inertial frame of reference. A non-inertial frame of reference is one that's accelerating. So let's suppose that you're on a train and you put a ball on a table. Well, it looks like the ball is just sitting still. The train starts going that way, and it looks to you like the ball's going that way. The ball's just trying not to move, and the train is accelerating out from underneath it. That's called a non-inertial frame of reference, and the math is a whole lot more complicated when you're dealing with a non-inertial frame of reference. So acceleration is a change of either speed or direction. It takes you 24 hours to go 25,000 miles, which is 1,000 miles an hour, but also it takes you 24 hours to go around 360 degrees. So it's such a very slight change of direction, you don't feel that acceleration. At the North Pole and at the South Pole, you wouldn't feel it either, but you'd realize, oh, yeah, I'm turning. Because you see all the stars up there. And they would look like they're turning compared to you. So there are a number of quantities in physics that you have to have a frame of reference for. So, what is your position? What's the answer to the question? Question would be, compared to what? What's your position? I'm right here. Yeah, but where is that? Compared to the North Pole, I'm this many miles. Compared to the equator, I'm this many miles. Compared to New York or whatever. You need a frame of reference. What's your position? Okay, what's your velocity? Velocity is a change of position over time. So what's your velocity? Compared to what? Momentum is your mass times your velocity. So what's your momentum? Compared to what? Suppose that you are sitting on an asteroid that's hurtling along at 60,000 miles an hour as compared to the Earth. And I ask you, how much momentum do you have? You say, none. Because you're just sitting on the asteroid and you don't feel anything. But compared to the Earth, you got a lot of momentum. And likewise, kinetic energy, you'd say, compared to this asteroid I'm sitting on, I don't have any kinetic energy. I'm not moving. But compared to the Earth, when you smack into it, you'll realize, oh, well, you won't realize because you'll be dead. But somebody else watching you would say, oh, that person sure had a lot of kinetic energy. Potential energy is the energy of position. Do you have any potential energy? Well, if somebody suddenly pulls a chair out from under you, you realize, oh yes, I did have gravitational potential energy. Or if you're standing on the edge of a cliff, compared to that cliff, you have zero gravitational potential energy. But you jump off and you realize, oh, I had a lot of gravitational potential energy. So frame of reference is crucially important when you're studying motion. It's always compared to what? So there are some equations that are used to describe motion. I just went over that. The study of motion, of how things move, is called kinematics. There's a different study for how things change their motion, but kinematics has to do with just describing the position of something, the velocity of something, and so forth. It's a study of how things move, and it's going to involve several different quantities. One is going to be the position, which you could call the distance or displacement, and I'm not going into the details here like I would in a physics class. Distance is just how far, displacement is how far in a specific direction. So as I always would tell my students, displacement means how far from this place to that place. For those that are watching on video, that's a typical South Louisiana accent, from this place to that place. So that's normally going to be represented by either D or X, and some people use the letter S. I don't know why they use S, but they do. And then velocity is involved. It's usually represented by a V. Acceleration is usually represented by an A, and time is usually represented by a T. And the most common measurement of time is going to be the second, not the minute or hour. Of course, when you're driving along, you say, I'm going this many miles per hour, kilometers per hour. But typically, when you're doing a physics calculation, you don't do per hour, you do per second. And then when you're trying to deal with the initial conditions and the final conditions, you normally are going to put subscripts. What's your velocity? Well, what was it when I started? And the way you indicated when I started, you put a v with a little subscript, either 0, v at time 0, or v with a little subscript initial, subscript I for initial. So you can also have d0 or d initial, x0, x initial, s0, s initial, and then the final position or velocity or whatever is going to be df for final, x final, s final, v final, a whole bunch of different things. So there have been people doing experiments on this for hundreds of years, and they've come up with 3 basic equations, and one of them has several different variations. So y'all going to get a test right at the end of it. No, that's not true. I'm going to show you what the equations are, but don't worry about how you get them. First equation of motion indicates if you started out at a certain initial velocity, you accelerated for a certain amount of time, what's your final velocity? So v final is v initial plus acceleration times time. That's the first equation of motion. The second equation, there's 4 different variations. If I want to know what's my position, my displacement, distance, or whatever, well, it's whatever I started with plus the velocity times the time. So d is equal to vt. But then if I don't know exactly how much acceleration there was, but I do know my beginning velocity and my final velocity, if I was accelerating, then I would average out the beginning and final velocity, so that's the second one. Beginning velocity plus final velocity divided by 2, that gives you the average, multiply that by time. The next one, if your problem doesn't mention anything about velocity, well, when you work out the math, you'll see where this came from, but it's d is wherever you started plus 1/2 at squared, and then when you want to bring in every possible variable, that's this one. Where you ended up is where you started plus your initial velocity times the time plus 1/2 times the acceleration times the time squared. So you all ready for that? You ready for a test on this? Okay, Cindy said yes. And then there's one more equation that doesn't have any variations. This is the only one that doesn't mention time. So it's very useful if you know this is how fast you were going at the beginning and how fast at the end, and you either know the acceleration or well, anyway, you can use this to figure out all of the other quantities. Any one of those, you have one missing quantity and the rest are known, so you just plug in and do a little math and find out what's the answer, what's the missing quantity. Those were one-dimensional kinematic equations in a straight line. Well, how much motion is just one-dimensional? Not that much. If I throw a ball over there, it's going that way, but first it's got to go up and then it's got to come back down. So that's 2-dimensional motion. And you could also have 3-dimensional motion. It's really not that complicated, though. What you do is you separate the x and the y. And you work out the x and you work out the y, and you come up with the answer for each of those two, and then you put them together. Have you all heard of the Pythagorean theorem? Okay, Pythagorean theorem says in a right triangle, the square of the first side plus the square of the second side equals the square of the hypotenuse, which I like calling it the hippopotamus, but my students would be amused by that, the hippopotamus leg theorem. So you can solve for the missing quantity just by using the Pythagorean theorem. And if you want to find out the direction, you got to get into a little bit more math. This would be like Algebra 2. There's some things called sines and cosines and tangents. I'm not going to do that in this class. But if you really want to solve these problems, you need to be able to do some sines and cosines and tangents. Then the question is not just how do things move, but why does motion change? This is called dynamics. It has a great deal to do with forces. A force is a push or a pull. There's also something called an unbalanced force, which is where you're pushing, nothing pushes back, or you're pulling and nothing pulls back. That's going to cause a change of motion. But then you also may have something pulling back against you or pushing back against you, balancing your force. In that case, okay, you're not going to have any acceleration. So an unbalanced force is also called a net force. And if you want to go out and catch butterflies, what do you have to exert? A net force. Scoop up your butterflies. Okay, so the balancing force can be either a push or a pull. So if I hold an apple in my hand, the earth's trying to pull it down, and I'm balancing that with an upward force, a push. Or if the apple's hanging on a tree, the earth's trying to pull it down, instead of a push upward, you have a pull upward on the stem. So balancing force could either be a push or a pull. But we're going to see later on Newton's third law is not the same as that. There are 4 fundamental forces that scientists have identified. The first one, of course, is going to be gravity. That's pretty obvious, right? You drop stuff, it falls. The second one is called electromagnetic. Now, gravity, as far as we've seen, is always a pull. Never seen gravity push. If you could come up with a way to make gravity push, you could develop a new industry. You could have flying cars and go to the moon and all of that just by reversing gravity. But we don't have the ability to do that. And I can't see the clock from here. I'll bring my phone over here so I can glance occasionally. Okay. So gravity always pulls. Electromagnetic can either be a push or a pull. Most of the everyday forces that we experience have to do with the electromagnetic force. There's a third force, which is called the strong nuclear force. Every atom in the universe that has 2 or more protons has got a force of repulsion inside there. 2 positive things put together are going to try to do what? Fly apart. But they don't. Why not? We don't know. Let's put a name on it. So scientists have decided whatever this unknown force is, let's call it the strong nuclear force. It's what keeps the nucleus together, even though the nucleus shouldn't stay together. Well, I think Colossians chapter 1, I believe, 17, says he is before all things, and in him all things hold together. So Jesus said your heavenly Father knows how many hairs you have on your head. He even knows how many protons you have in your atoms, keeping all of those together. God is just so far beyond our imagination. Okay, so the strong nuclear force is what holds the atoms together. The weak nuclear force is, well, the strong nuclear force holds them together until it doesn't. Every now and then you'll have a nucleus of an atom fly apart in something called beta decay. And why does that happen? Oh no. Is the strong nuclear force a push or a pull? Well, it's a pull to keep the atoms together. Is the weak nuclear force a push or a pull? We don't know. This is something that's far too small to see. We just say, oh, well, look, that changed into a different element. What's the new element? What are its properties? How'd that happen? Well, let's come up with a model of how it happened. We can't actually see it happen, though. Then there are forces that we deal with every day, except for gravity, of course. They're actually some variation of the electromagnetic force. So, for instance, if you experience friction, you feel your hands rubbing against each other, the atoms are not actually touching each other. The outer edge of an atom is identified by where its electrons are, and you would have to furnish an incredible force to make the electrons hit each other. And you don't have that much force available. So they're just right next to each other, and when you rub your hands, you're putting kinetic energy in there, and it comes out as heat, but they didn't actually touch each other. And so if you have a rope pulling, the atoms of the rope, they're pulling due to electromagnetic attraction, but do they actually touch each other? Probably not. If your hand is pushing an object or 2 objects hit each other, this is transmitted through what seems to be direct contact, but our understanding is at the subatomic level, the atoms don't actually touch each other. They just feel like it to us. Those are contact forces. And then there are field forces, which is going to be electromagnetism and gravity, that can go through what seems to be empty space. How can you tell what the gravitational constant is? The law of gravity that I've written a bunch of times, including up there, force of gravity between two objects is a gravitational constant times the mass of the first object times the mass of the second object divided by the distance between the centers squared. That's what Newton discovered 400 some years ago. It breaks down when you get up to super high velocities close to the speed of light, but our circumstances we perceive all the time, classical mechanics, that works fantastic. So if you want to know how much the force of gravitational attraction is going to be between two objects, those are the things you need to know, which means you need to know the gravitational constant. It's actually not that hard to measure. There's something called a Cavendish balance where you have, well, come back up here. You have a wire with a known resistance to twisting, and you have, like one of those mobiles for the little kids, you have a bar and two masses on the end. And then you have two other masses. These are pretty good size objects, you know, probably lead balls, 20, 30 pounds, something like that. And you put it in an airtight container, and hopefully you suck the air out of it so you don't have to worry about air resistance in there. And you have an adjustment from the outside. It's all sealed up, glass walls so you can see. And you gradually bring them closer, and at a certain point, they're going to start to move just a itty bitty bit. And this wire has a measured resistance force to twisting, so it's called a torsion wire, and you can actually see the thing move, and you put mirrors on there and use lasers, and you can see the angle that it moved, and you can calculate the gravitational constant. This is how we know it, by direct observation. When I was in college, we did that one time. That was kind of a cool experiment, you know, using a Cavendish balance. So, moving along, Newton discovered some laws of motion when he was at home waiting for the Black Plague to go away. The first law of motion is called the law of inertia. Inertia means resistance to change. Inertia is not a force, it's a resistance to force. So unless an object is acted on by an unbalanced force, it's going to keep doing what it's doing. If it's moving, it'll keep moving. If it's not moving, it won't start moving. So, as I like to put it, stuff keeps doing what it's doing. Unless you force it otherwise. That is, no unbalanced force equals no change. His second law of motion says, well, what if there is an unbalanced force? What happens then? Then the objects are going to experience an unbalanced force will accelerate. They'll change either speed or direction or both in a manner that's directly proportional to the size of the force and inversely proportional to their mass. So if there's no unbalanced force, there's no change. If there's yes unbalanced force, there's yes change. How much? Oh, here's the equation. So if you know the amount of force and you know the mass, you could calculate the acceleration. If you know any two of these, you can calculate the third one. It works perfectly in classical mechanics. Now, when you get up near the speed of light, then all sorts of weird things happen to mass. So it breaks down, but I'm talking incredibly fast, you know. The speed of light is about 300 million meters per second. It takes about 1.25 seconds to get to the moon. And it took the Apollo astronauts, 3 days to get there? So the speed of light is pretty fast. Okay, so that's the second law. Now the third law, I used to worry about getting in trouble with my students, and those that are watching this online, if you're from Chicago or something, you won't realize the way that we pronounce things down here in South Louisiana. Okay, Newton's third law of motion. This says for every action, that is for every force, there's an equal and opposite reaction. It's not necessarily motion. If I push on an elephant, the elephant pushes back on me just as hard, but who's going to move more? Me. The elephant's got a whole lot more mass. The force is equal and opposite. Okay, so the motion is not necessarily going to be equal and opposite. You're pulling on the earth just as much as the earth is pulling on you. So who moves more, you or the earth, when you jump off a cliff? Well, you move a whole lot more because your mass is a whole lot less. So I used to tell my students, when you go to the zoo, you see the monkeys at the zoo. The monkeys are mad because they're in a cage and you're not in a cage. So the monkeys want to get even with you. And what do? They pick up monkey poo and they fling it at you. Well, it's turds. I'm sure y'all have heard turds, right? Okay. Well, Newton's third law of motion says if the monkey throws this, then the monkey goes backwards. Out in space, if you watch the movies, you'll see that somebody's maneuvering around with a little air jet. In order for the air to go that way, there's an opposing force trying to make the person go the other way. That's Newton's third law of motion. Whatever goes in one direction, there's going to be an equal and opposite force in the other direction. Not necessarily equal and opposite motion, but equal and opposite force. So, as I said before, a balancing force could be a push or a pull. Well, Newton's third law of force, the equal and opposite, is always the same as what you applied. The reaction to a push is always a push. The reaction to a pull is always a pull. So if I push on this wall, the wall pushes back on me, it doesn't pull me. If it did, I'd get sucked in. And that wouldn't be a very pleasant thing. That's what you do science fiction movies about. So speaking of Newton's third law, how do rockets fly out in space? People frequently think that a rocket flies by pushing on the atmosphere. That is not the case. A rocket flies by pushing inside of itself. When you have combustion going on inside this engine, there's an expansion force in all directions. Well, the front of the engine stops it, the middle of the engine stops it, the back of the engine is open, so it can't push back. So the expansion of the expanding fuel is pushing on the front is pushing back, the expanding fuel coming out the back, there's nothing to push back against it. So this is actually where the push is going on. It's inside the engine. Rockets fly better in space than they do in the atmosphere because there you have air resistance and friction messes you up. Next question. This is another Newton's third law of motion thing. How do airplanes stay up in the air? Has anybody ever heard of Bernoulli's principle? This is one of the things I remember from a high school physics class. Mr. Brown always used to, not always, but when he talked about this, he'd say, how do birds fly? Bernoulli. Well, it has to do with flying. Actually, the force is called the Magnus force, but it's Bernoulli's principle. If an airplane is just sitting on the runway, of course, it's not going to go up in the air. It's got to be moving forward. As it's going forward, well, the reason for that is the engine is pushing air backwards and the air is pushing the plane forward. So it could be a jet engine, it could be a propeller engine, but it's pushing the air backwards. So when the backwards force of the air and the forward force are equal, then the thing just quits accelerating. This will happen when you're going fast enough because of air resistance. If there was no air resistance, you'd keep going faster and faster and faster and faster and faster. But after a while, if you're going forward, air is dragging on you enough that you can't go any faster. It's like if you're a skydiver, the force of gravity is pulling you downward, and the faster you go, the more resistance force there is, air resistance pushing you up. After a while, the downward force of gravity and the upward force of air resistance balance out. Does that mean you stop and hover in midair? No, it means you quit accelerating. Newton's second law has to do with acceleration. If there's an unbalanced force, you accelerate. If there's no unbalanced force, first law says you just keep doing what you were doing. So if you're going downward 120 miles an hour and air resistance balances out gravity, you keep going 120 miles an hour. There are a lot of people that love to skydive. I'd be glad to take pictures from the ground. I don't think I want to join them though. Some of y'all are probably skydivers, right? No? Okay. I see no reason to jump out of a perfectly functional airplane. Okay, so horizontally, you're going forward and the air is pushing back, and after a while, when the forward thrust of the motor exactly gets matched by the backward thrust or by the drag force of the air resistance, you quit accelerating. In the vertical direction, air molecules are continually pushing every which way. But have you ever noticed the shape of an airplane wing? It's got a bit of a curvature to it. So it's a little bit inclined to the air anyway, but then the curvature on the top, the air has got to go faster. It's got to go a longer distance in the same amount of time. So it has to go faster, and it doesn't have enough time to push downward. The air on the bottom of the wing is pushing every which way, including upward. The air on the top of the wing is pushing left and right, but it doesn't have time to push back downward. So you get a net force called lift, or it's the Magnus force. So the difference in airspeed caused by the seams on a spinning baseball work by the same principle. Does anybody throw baseballs in here? You ever pitch or something like that? Well, do you know what a baseball looks like? It's not perfectly round. It's got raised seams. That's deliberate. So as you throw the ball and you spin it, on one side the seams are going faster that way and the air bunches up against them, so the air is moving slower. On the other side, the seams are dragging the air this way and the air on this side is moving faster, and so it doesn't exert as much force, so the ball goes like that because of the curvature. Likewise, a soccer ball has got seams in it. It has grooves. Y'all ever heard the expression bend it in soccer? If you know what you're doing, you can kick a soccer ball and get it to spin, and as it goes through the air, it's going to do the same thing as a curveball in baseball. There was even a movie called Bend It Like Beckham about soccer. Well, it's amazing what soccer players can do, and they're taking advantage of physics, Bernoulli's principle, the Magnus force, air resistance, drag, all of this kind of stuff. Okay, this is something that's a little harder to visualize sometimes. Momentum is the product of mass times velocity. Well, there's a principle that really is what led Newton to some of his laws. It's called the law of conservation of momentum. If I have two objects hit each other, they had a certain momentum this way and a certain momentum that way, and mass times velocity including direction, and afterward they're going to either fly apart or stick together. But if you take this momentum plus this momentum before, put them together afterward, it's still the same total amount. It may total up to zero if they had exactly equal and opposite momentum, or it may be that the object is moving off that way or moving that way. So this is pretty obvious, I think, except when two things collide and they go bang, well, that's some of the momentum. Air molecules are always going like this. So even as the objects are going through them, two cars are coming together, the air molecules are going like this. While the cars hit, they also make those air molecules pick up an awful lot of that momentum, and that's the bang you heard. They've gotten some kinetic energy, which ties closely to momentum. But then also, this is assuming the law of conservation of momentum. This is assuming you're in an isolated system. It's in a box and nothing can go anywhere. Well, is the Earth really like that? No, energy flows out into space all the time. So some of the energy is going to flow out into space in the form of heat. Okay, let's talk about conservation of angular momentum. I couldn't find a picture. I'm so thankful to Wikimedia Commons. People put pictures on there and they give you blanket permission to use them as long as you attribute the person that created it. So I don't want to have any problem where somebody says, that's a copyrighted picture. So I find things that are not copyrighted. Couldn't find a non-copyrighted picture of a figure skater spinning, but this was two girls standing on a turntable, and when one of them has a weight out at arm's length and you try to spin the person, they're going to go pretty slow, right? But then if they pull the arms in, what do? Figure skaters do this all the time. Cut the arms out, pull them in. Whoosh. I don't know how they don't throw up. I couldn't handle that. Okay, so the smaller the diameter, then the faster it goes, or the slower it goes, the larger the diameter. There's a cause and effect connection between those things. So a moving object has linear momentum, a rotating object has angular momentum. Here's an interesting thing about what's happening to the Earth and the Moon. It's not a rigid body, but here's the Moon going around the Earth, and the Earth wobbles a little bit, but the Moon is pulling the tides, and the tides are dragging back on the Moon, the ocean tides, and as a result, the Moon is gradually slowing down, gradually, and also the Earth is gradually slowing down, itty bitty bit. But because of the law of conservation of angular momentum, the Moon, as it slows down, is gradually moving away from the Earth. It's about 4 centimeters a year, which is 1.5 inches, not quite 2 inches. The Moon is gradually moving away from the Earth, and it has to do with the law of conservation of angular momentum. Now, here's a good question for people that say we've never been to the Moon. You ever heard anybody say, we never actually landed on the Moon back in the late 60s, early 70s? We didn't have the kind of CGI technology back there, computer graphics imaging, that you would need to do this kind of thing. Our technology was really primitive as compared to what we have today. So nobody could have faked that stuff out. But then here's another thing. We left shiny stuff up there. So anybody with a powerful enough laser, and this has been done by a bunch of agencies, government agencies and universities and so forth, if you have a powerful enough laser, you start your timer, trigger it to go to the Moon, and see how long does it take to come back. The speed of light is known, very precisely defined. It's just under 3 times 10 to the 8th meters a second. It's 2.999 whatever. And you see how long did it take to come back, and you see how far away is the Moon. The Moon is gradually receding, and we know this because we went up there and we left stuff. All right, well, the Moon is gradually moving away from the Earth. So work backwards through time, it would have been closer and closer and closer to the Earth. Approximately 1.5 billion years ago, the Moon would have been scraping the surface of the Earth, assuming that it was never faster than it is now. And it probably would have been faster back then, but assuming it's no more than that, okay, does anybody know how old the Earth is supposed to be? About 4.5 billion years. Does anybody know when life is supposed to have begun? About 3.5 billion years. But this would have been 1.5 billion years. The Moon would have been scraping the surface of the Earth. You'd have to duck every so often because look out, here comes the Moon. Well, it's impossible. So the Moon shows that the Earth can't be more than 1.5 billion years old. In fact, it's got to be a lot less than that, because if the Moon was too close, it would break apart anyway. So this is going to put the age of the solar system at far less than 1.5 billion years. Later on, I'm expecting we'll get around to talking about the age of everything, but it just ain't as old as evolution says. Have you ever noticed how a gyroscope, when it's spinning, it tries to stay upright, and then eventually it's going to start to wobble, and eventually it's going to fall over? Or if you're on a bike or a motorcycle and the wheels are spinning really, really, really fast, it's a whole lot easier to stay upright than if you're going slower. And the motorcyclists going around the curve, you say, well, they're leaning over like that, but they really have good tires, good friction with the road on their tires. But part of what's helping them stay upright or not fall over is the law of conservation of angular momentum. When you want to find out what's the direction of angular momentum, it does have a direction. You use what's called the right-hand rule. You take the direction of spin and you wrap your right hand around, and your thumb of your right hand points in the direction of the angular momentum. So if there's a spinning gyroscope, it's going like that, and your thumb is pointing, that's the direction of the angular momentum. It wants to keep going that way. Now you can force it to change by applying an external force, but until it gets enough external force, it's not going to change direction. So that's why a gyroscope can stay spinning for so long. There's friction in there, so it gradually slows down and then gravity pulls it over. But have you ever thought about how we keep satellites in orbit from tilting over, from tipping over? We put gyroscopes on them. They're driven by motors, so they never slow down. They just keep going same direction, and that's going to keep the angular momentum pointing in the same direction so the thing doesn't gradually tip over. So you can use Newton's laws and the equations of kinematics to predict the motion of any object in classical physics. Does anybody remember, I've talked before about some of the mistakes Aristotle made? Famous Greek guy, he said, I'm the smartest man in the world, and everybody else said, okay, yeah, we'll follow Aristotle. Aristotle said it, I believe it, and that settles it. Well, Aristotle made a bunch of really dumb statements. One of the things that he said was there's no such thing as atoms, which we'll get to probably next week. Another thing he said is that heavier objects always fall faster. Another thing he said is that objects possess an innate tendency to come to rest and then stop. And he said that the stars are all the same distance from the Earth. So he said some dumb stuff. He also said some good stuff. He invented the logic that we use today, the Aristotelian logic. But this is why Aristotle was wrong about falling objects. The law of gravity, as Newton discovered it and formulated it, is the force of gravity between two objects is gravitational constant that you can measure times the mass of the first object times the mass of the second divided by the distance between the centers squared. Okay, so plugging in what the objects are, you got an object, come back up here. You got an object and you got the Earth. So the force of gravity is the mass of the object times the mass of the Earth divided by the distance squared. And Newton's second law said F equals ma. Is this working or is my battery dying? I hope not. Give me a second, y'all. No, okay. So Newton's second law says F equals ma. Well, what force are we talking about? The force of gravity. So let's plug it in and say the force of gravity is the mass of the object times its acceleration. Okay, does that make any sense so far? I'm just plugging in stuff. So, since that's the force of gravity, it's a mass of the object times its acceleration. Put that in on the left side, and on the right side we have gravitational constant times the mass of the object times the mass of the Earth divided by the distance squared. Mass of object cancels out on the left and right, so what you're left with is the acceleration depends only on the Earth. It doesn't depend on the object. Of course, Aristotle's problem was he was ignoring air resistance. There's certainly going to be friction against the air all the time, but he just didn't think it was an important thing to worry about. So the acceleration of gravity is a characteristic of the body pulling on it, the Earth, not on the object. Now, if the object was like the size of a planet or a moon, then okay, yeah, that would be different, because the mass of that object would be something we couldn't just ignore. But for stuff that's probably less than the size of a mountain, the acceleration of gravity is due to the Earth, not the object. Has anybody ever thought about this question? Are you weightless in space? I've had my students ask me this, and movies will show you this. You know, you got to get away from the gravity of the Earth. There was a movie called The Space Between Us, and this guy was raised on Mars, and when he came to the Earth, the gravity was too much, and he was getting sick, and he was about to die, so they had to put him out in space where gravity ends, and then he was okay once gravity is zero. Yeah, okay. Is gravity really zero out in space? If there was no gravity in space, what would the moon do? It'd go flying away. What would the Earth do compared to the sun? We'd go flying away. There's definitely gravity out in space. So when you're sitting on the surface of the Earth, like you are right now, you're about 6,400 kilometers away from the center of the Earth. Well, let's say you go into an orbit 300 kilometers up, which is a typical orbit, 150 miles or something like that, 160 miles. So using the law of gravity, which is a force of gravity, is gravitational constant times your mass times the mass of the Earth divided by the distance between them squared. Let's compare the ratio of how much gravity there would be on the Earth, 6,400 kilometers, as opposed to out in space, 6,700 kilometers. So you work the math out, and you find out that it's a ratio of 40,960,000 to 44,890,000. So it's 91.2%. If you're 300 kilometers up, you still have 91.2% of the weight you have on the surface of the Earth. How can that be? Oh. Well, do you feel it? You still have the weight, but you don't feel it. Right now, think about, do you actually feel your weight? What you feel is a chair pushing up on you. The Earth is pulling you down, you're pulling the Earth up, but if there was no chair and you were falling, people that have gone skydiving say there's no feeling of falling. You just feel the air rushing past you, but if not for that, you wouldn't feel like you were falling. The reason you feel something is because you're pushing on the chair and the chair is pushing up on you, and that's what you feel. Or, I'm not sitting in a chair, but I feel the Earth pushing up against my feet. Now, of course, if you hold your arms up here, yeah, that's different, but just let your arms hang, and what you're really feeling is the push of whatever's preventing you from falling. So there's some sort of an object that's pushing you upward. The reason the astronauts feel weightless is there's nothing pushing them upward. They're in that space capsule and they're falling, but the space capsule is falling just at the same rate they are. Why don't they hit the Earth? Because they're also going forward. There's a constant interplay between your inertia, your momentum going forward, versus gravity pulling you down, and it forces you to go into a curved path like that, so you never quit falling. And since nothing is pushing back up against you, you feel like you're weightless, but you're really not weightless. Okay, there's also something that's kind of related to that. It has to do with rotational motion. Has anybody ever heard the term centrifugal force? Ain't no such thing. If there was a centrifugal force, that means center fleeing. It's a Latin term, center fleeing force. Well, if there was such a force, it would throw something straight out. So let's say I've got an object that's going around, like when David had his sling. The way it worked, it was a little pouch and you had two strings and you swing in the rock, swing in the rock, swing in the rock. When he let it go, which direction did it go? Did it go straight out from the center of the circle? No, it kept going forward. This is Newton's first law of motion. Once you remove the unbalanced force, it just keeps doing what it's doing. So I'm swinging and I'm swinging and I'm swinging it. If I let go right here, it's going to go that way. If I let go right here, it's going to go that way. So there's no force that's trying to push the thing directly out from the center, but instead inertia tries to make it go in a straight line. There is a force that's called centripetal force. That's Latin for center seeking. Centripetal force is continually pulling you in toward the center. So you have inertia trying to make you go that way, centripetal force trying to pull you that way, and so you add those two forces and it just puts you into a continual circular motion until you remove whatever the centripetal force is. When you're on a merry-go-round, the centripetal force is very likely caused by friction between you and the seat. Or you may be holding on to the bar. It's the tension between you and the bar. But when you let go, you don't go straight out from the center. You go forward in whatever direction you were going at the instant that you let go. Okay? okay? So there's no such thing as a centrifugal force. It's a centripetal force. Now here's another one. Nancy knows about this already. It's commonly called the Coriolis force. Anybody ever heard of that? People will tell you that toilets swirl the opposite direction in the southern hemisphere. Y'all ever heard that? Okay, it's false. There was a French guy, scientist named de Coriolis, I don't know how you pronounce his name, but he noticed something observing the weather patterns that in the northern hemisphere, large masses of air tend to swirl that way. In the southern hemisphere, they tend to swirl the opposite direction. And so people say, there you go, toilets are going to swirl the opposite direction. No, this is because of the fact that the Earth is spinning, and so air moving at the center of the Earth at the equator is going about 1,040 miles an hour east. And likewise, water at the equator is going about 1,040 miles east. But when you move up and you get closer and closer toward the North Pole, how fast east is the North Pole moving? 0. So you're going from 1,040 at the equator to 0 up at the North Pole. So as that air moves away, it's moving sideways at 1,040 miles an hour, and it gets a little bit away. It's still trying to move sideways at 1,040, but the planet underneath it is not turning as many miles per hour, and it goes further, and the planet is turning even less. And so somebody on the ground says, whoa, look at that air swirling over there. No, the air is trying to go in a straight line. It's just if you're an observer on the surface of the Earth, then you think the air is swirling, but if you'd put a balloon in that air, it would actually keep going just a straight line. So the Coriolis effect is not a force. The air is not really changing direction. It's moving sideways faster than the Earth as it gets further away from the equator. And likewise, ocean currents, the water is moving at 1,040 miles at the equator, and if the current flows away from the equator, well, the sea bottom is not going as fast. And so the water follows what we would view as being a curved path when you get further away from the equator toward the north or toward the south. It's just because we're using a different frame of reference. A lot of people have got this idea that drains always go one direction in the northern hemisphere and the other direction in the southern hemisphere, and people think toilets go one way in the northern and one way in the southern. No, that's not at all the case. This has to do with a very large body of water or air, maybe hundreds of miles across, and it's moving away from the equator. Well, how big is the water in your toilet? Is it moving away from the equator? No, the Coriolis effect has no effect on what's in your toilet. This is something that has to do with large air masses. And this is not the only thing that affects the weather. Anybody ever heard of the butterfly effect? If a butterfly flaps its wings in China, it can change the weather in Ohio. There's millions of factors. We don't know what all of them are. A lot of it is the sunlight hitting the earth and warming it up unevenly here and there, and then the tides hitting the ocean and moving the heat around. But this is one of the factors, the Coriolis effect. Okay, let's start talking a little bit about waves. This is a wave. So what's this? This is a microwave. Har, 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 har. There are a great many physical objects, such as water and air molecules, that they move in waves. Boom, 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 boom. So they transmit energy, and the particles vary very predictably in their position and in intensity of motion, but the particles almost never travel all the way from the source of the energy to the receiving end. So right now, this would be really gross if it was true. As I'm speaking, are air molecules coming out of my mouth, moving across the room, and eventually getting into your ears? Ugh, no. Air molecules move, hit the next air molecule, which hits the next air molecule, which hits the next air molecule, which hits the next air molecule. and the molecules out of my mouth never get to you. There are two main types of waves. They're mechanical and electromagnetic wave. There's a third concept called matter waves that we're going to get to a little bit later. It describes what's called the wave-particle duality of matter and energy. The mechanical waves are things that require some kind of a medium. They include sound, water waves, seismic waves in the Earth's crust, things like that. They require some kind of a medium to transmit the energy. So for instance, sound travels because a molecule hits the next molecule, which bumps it, makes it hit the next one, bumps it, and so forth. And the molecules don't have to travel all the way across the room. But generally, the denser the medium, the faster the sound travels through it. I want to give you an illustration of something called a longitudinal or a compressional wave. Y'all have seen these, I think, right? Everybody loves a slinky. Are the particles going all the way from one of my hands to the other hand? No, but the energy is. The particles are pretty well trapped in place by the physical structure of the slinky. And you can get a really long slinky, and that's kind of cool too. I used to have one of these set up with a speaker on my classroom ceiling, and it would stretch all the way down, and you could actually see what's called standing waves at a certain place, and the energy kept going, but the particles in certain places hardly moved at all, but the energy keeps going. And then there's another kind of wave. It's called a transverse wave. So I'm going to need somebody to help me with this. Need somebody to come up here and help me. I bet Cindy would like to do this. And I'm going to try to get it on camera. So we've got to hold it up pretty high. About that high. And please don't unplug my thing. Okay. Okay, so you see how the spring is going up and down and up and down and up and down and up and down. But Cindy could feel some energy from me. The energy goes that way, but the particles go that way, up and down and up and down. It's really neat if you do this. This will stretch out to like 30 or 40 feet. And if you have it on a smooth floor, you can set up all these neat looking waves. Okay, you shake it a little bit. Okay. Now give it some more energy. Go faster. Okay, well, you can go up and down more, but also go faster. Try to go twice as fast. Notice now we're getting more than one wave in there. Just, okay, you hold it, I'll do the shaking.
You do it.
Whole lot of shaking going on.
Oh.
I have to put in more energy to do that. What's that?
You get more waves.
Get more waves. So, thank you. So I have waves of a higher frequency, but a shorter wavelength. Shorter wavelength means more waves per same distance. So in a transverse wave, the particles move up and down or perpendicular to the direction of energy. Energy goes there, particles go there. Compressional wave, energy and particles go that way. On the surface of a body of water, if it's not a windy day, what's the path of the water molecules? You ever notice this? The water molecules are going up and down, but the wave is carrying them over there and then they come back. So the water molecules are actually following sort of an oval motion. If you don't have any wind, of course you probably wouldn't have waves either, but if you don't have wind, then the water molecules are not going to keep going and going and going and going. Like if you put a fishing bobber out there, it's just going to go like that, unless the wind comes along and blows it. So water waves are a combination of transverse and compressional or longitudinal waves. And then another kind of wave that's particularly important is called an electromagnetic wave. Could I ask somebody to get me some more water, please? Water.
Who's going to get me some chocolate?
Yeah, Just a glass is fine, a cup. Okay, electromagnetic waves are actually three-dimensional. So the little spring that we were demonstrating before, you'd have to go up and down and also left to right at the same time. So it's hard to visualize this, but the electromagnetic wave goes up and down, and it also goes in and out at the same time, three-dimensional, as it's traveling along. Thank you very much. So it's not something you could look at under a microscope and say, oh yeah, there's the wave. It's an electric and a magnetic field, and it has an intensity that goes from a maximum in one direction through zero, maximum other direction, back and forth. And meanwhile, the other way is going maximum zero, minimum zero. So this is a graph, and that's how we have to represent these things. In fact, if I go back to the compressional wave, we normally graph these as if it was a transverse wave. The particles don't actually go up and down, up and down, up and down like that. What we're showing is the intensity. So in an electromagnetic field, it's actually three-dimensional, and they're perpendicular to each other. Oh, well, show me which way the magnetic is and which way the electric is. I don't know. Nobody knows. This is a result of Maxwell's equations. We graph those things, and this is the kind of graph we get out of it. So you really would need to use the x and the y and the z axis of the coordinate system invented by Descartes. Y'all remember Descartes? Okay, don't put Descartes before Deshorse. No. The people that are watching this just groan. Okay, here are the characteristics of waves. The highest point on a wave is called the crest. The lowest point is called the trough. There's a crest up top, there's a trough down at the bottom. The places where the wave crosses the center line are called nodes. So here's a node, here's a node, here's a node, here's a node, there's going to be another node over there in a minute. And then the distance from the center line to either the crest or the trough is called the amplitude. It's half of the height. Then if you go all the way from crest to trough, it's called wave height. So I never have figured out when somebody says there's 2-foot waves on the lake. Does that mean, is that the amplitude or the wave height? I don't know. I guess it's the wave height. One day I was out with my neighbor. We took my boat out and it was a windy day. I have a little bass boat. And so we went a little ways and said, nah, it's too rough out here. Let's go back. So we looked and there was a capsized one-man sailboat about a quarter mile away. And so my neighbor says, there's somebody in the water. I said, no, that's a basketball or something. No, it was a guy's head. He wasn't dead. So he had just bought this boat, and don't mess with the waves. He had just bought this boat and went out there on a one-man sailboat on a windy day with no life jacket. The thing turned over and he was trying to swim back to shore. It's a good thing we came along. He would have drowned. And you ever think about this? When Peter was out there and Jesus is walking on the water, Jesus says, come. Peter starts walking. And the Bible says when he saw the wind, he became afraid. So Peter was not concerned about the waves. He said, you can't walk on the water when it's windy. That's kind of strange, right? Go look that up. That's what what it says. When he saw the wind, he became afraid. Okay, so moving along. The distance from the crest to the trough is called the wave height, which is twice the amplitude. Then the distance from any point on a wave to the corresponding point on the next, like from here to here, or here to here, or here to here, that's called the wavelength. It's the length of the wave. And it's going to be measured in some fraction of a meter. Although AM radio waves, which nobody listens to AM radio anymore, those can be thousands of meters long. They're very low frequency. Low frequency equals long wave. There's even a kind of wave that they use for military communication. It's known as an ELF wave, extremely low frequency. So go out there and find the ELF wave. That must be how Santa communicates, right? Using ELF waves. But waves go from extremely long to extremely short. They're measured in some fraction of a meter or in some multiple of a meter. Typically sound is going to be this long. Microwaves in your microwave oven is going to be like that. And then light is, see how big that is? Okay, so how frequently the wave repeats is called its frequency. That's measured in a unit called a hertz, after Heinrich Hertz, and it just means the number of times per second. So a lot of times they'll be written, instead of 8.4 times 10 to the third hertz, they'll do hertz is seconds to the -1 power, which is per second. So the frequency is often represented by the Greek letter nu. It's not a V. It looks like a V to us, but it's a Greek letter nu. That's a new one for all of y'all. And the wavelength is represented by a funny looking letter. It's called a lambda. To me, it looks like some kind of a dinosaur that's going to walk along. So the bottom wave here has twice the frequency, but half the wavelength of the top one. Frequency times wavelength are reciprocals of each other. So when one increases, the other one decreases. There's some characteristics of waves called reflection, diffraction, and refraction. So reflection is pretty obvious, right? You shine a light out something and it bounces back. The reason you're able to see is not that your eyes are putting out beams, but that light is hitting the wall and it's bouncing back in all directions. One of those directions happens to come into your eyes. You can make things reflect by curving what's reflecting them. The reflection is going to be at the same angle that it hit, but satellite dishes and telescope mirrors, they purposely use curved reflectors to focus the light or the microwave signal or whatever back to a single point. Have you ever noticed a satellite dish on somebody's house? It's got the curve and then there's a little thing where the wire hooks to. Okay, the waves coming in are focused right back to that point. It's called a focal point. Then there's a phenomenon called diffraction. When a wave goes through an opening or around a barrier, it's diffracted. Long wavelengths are diffracted more. So if somebody outside was playing a very high-pitched note out of that door, you wouldn't hear the high-pitched note that much. But if they were playing a bass note, you would hear it. Because when it comes through the door, longer wavelengths, lower notes, are diffracted more and they spread around. The high frequency is not diffracted as much. So I got a problem sometimes. I have to get in a certain position where the high frequency is going to hit me because my ears don't necessarily pick up all of the high frequencies. Okay, and then there's something called refraction. Oh, and diffraction also happens not just when something goes through an opening, but also around a barrier. So if you got an island out in the ocean and here come the waves, they're going to be diffracted around the island, and then there's going to be more waves on the opposite side. Might take a while for them to form, a certain distance away. Okay, refraction, the frequency of a wave, how frequently it repeats, is dependent on the source. Okay, that's going to be constant. So if something is putting out a 20,000 hertz wave, it's going to be 20,000 hertz. But the wavelength is inversely proportional to the frequency. The wavelength can change depending on what medium it's going through. So when a wave goes from one medium to another, its speed changes. Its frequency does not. But since its speed changes, its wavelength changes, and short wavelengths change more, and longer ones change less. So white light will split into a rainbow, which shows all of its component colors. Has anybody ever heard of Roy G. Biv? Yes, this is a memory aid that us dumb science teachers use to try to make people remember the sequence of visible colors. And I had a prism and I can't find it, so I guess we won't use it. Oh well. The sequence of visible colors: red, orange, yellow, green, blue, indigo, violet. You could probably pick out more than those 7, but that's just the standard that the scientists said. We'll say there's 7 colors of the rainbow, Well, speaking of the rainbow, oh, and speed of a wave. What's faster, light or sound? Light is much faster. Sound is typically around 330 meters a second through air. When the air is hotter or cooler, it's going to change the speed of it a little bit. But the speed of light in air is around 300 million meters per second as compared to 330. So the speed of light is about 900,000 times as fast as the speed of sound. Okay, because of refraction. Why is the sky blue? Well, the light comes down and the blue scatters all over the place. It's refracted all over the place. The red doesn't refract as much. So the blue is scattered a whole lot more than the red is, and therefore the whole sky looks blue. You can also get some interference between waves. When there are two sound waves that are in phase with each other, that is, the crest of one coincides with the crest of another, and the trough coincides with the trough. If they're exactly matched up, you're going to get a higher wave. So this is called constructive interference, where they match up perfectly. The wave is going to be much higher. You can also have destructive interference, where they are exactly out of phase. The peak of one, the crest of one coincides with the trough of the other. Then they'll cancel out. Most of the time the waves are going to be not exactly out of phase, so what you'll get is an interference pattern that looks something like that. And the interference patterns are very useful in astronomy and physics, where we're trying to see, was there a very slight shift in the light? We put the light through two different paths and beam it together and see, is there an interference pattern, to try to see if there's a motion of even the width of a few atoms. And this is also how we know that electrons can behave as waves, because electrons will form interference patterns even though we think of them as particles. Is an electron a wave or a particle? The answer is yes. An electron is a wave or a particle. Depends on what kind of experiment you do. In some experiments, sure, it acts very much like a wave. In other experiments, it acts very much like a particle. Okay, so back to electromagnetic radiation. This is called the electromagnetic spectrum. And there are things that have very long wavelengths, 1,000 meters or so radio waves. Some of them can be really long, the AM radio, but then you get shorter and shorter and shorter. And visible light is just a little itty bitty 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 part of the electromagnetic spectrum. I've had students ask me, and they think they're discovering something new, could there be other colors that we can't even see? Of course. Your eyes are able to take in and convert waves, electromagnetic waves, with a length of 380 nanometers to 760 nanometers. That's typically what a human eye can perceive. So the energy comes in and it's turned into an electrical signal sent to your brain. So, oh, I just saw some red light, 760 nanometers, or I saw some violet light, 380 nanometers. The shorter the length, the more it is toward the violet end of the spectrum. The longer the length, the more it is toward the red end of the spectrum. But past that, we see this much of the electromagnetic spectrum. Our eyes are designed for that. That's the primary colors that are put out by the sun. But there's an awful lot of other stuff that's all throughout space. There seem to be some kinds of animals that can pick up other colors that we can't. So does anybody ever remember using a yellow light on your porch so the mosquitoes couldn't see you? Yeah, mosquitoes can't pick up that color. So when it bounces off you, other people see you, but the mosquitoes say, come on, there's got to be some humans around here somewhere, and they're flying right past you. And other types of animals seem to be able to see, for instance, some types of insects and reptiles and bats seem to be able to see beyond red to the infrared range. And there are certain types of insects and birds that seem to be able to see in the ultraviolet. This is so unfair. In Africa, there's a little rodent called a dassie, and there's a predatory bird that flies over. It's called a kestrel. Well, the rodent tries to hide underneath the grass, but when it goes wee-wee, its urine reflects in the ultraviolet. And a kestrel is flying over, and the ultraviolet will penetrate through the grass. And the kestrel sees, somebody just peed down there, and goes down and gets it. That's so unfair to the poor little dassies. Well, God didn't ask my opinion about that. Okay, so things with the longest wavelength, lowest frequency. You see the wavelength is up at the top, the frequency's down here. Long wavelength, low frequency. Short wavelength, high frequency. The highest frequencies we call gamma rays, shortest wavelength, highest frequency. Gamma rays are deadly. They don't turn you into the Incredible Hulk and give you superpowers, they kill you. Your body is made out of carbon compounds, and these things, X-rays and gamma rays, they will destroy the bonds between carbon and other elements, and they'll kill the cell. So have you ever noticed when you go to get an X-ray, the X-ray technician leaves the room? Yeah, well, they do this all day, every day. And so they would get cancer pretty quickly. Now you go in there one time, okay, and you have your X-ray. They don't use gamma for diagnostic purposes. What do we use gamma for? Any idea? Well, one thing is cancer treatment. If somebody has a tumor on the inside of the body and it's inoperable, well, doctors will send a beam of gamma radiation through. And the attempt is to kill the tumor. Well, what's going to happen to everything on the way going and on the way past? It's going to die also. But the idea is the alternative is death. So you say, all right, I'll put up with the after effects of the gamma radiation. Because gamma is really, 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 really deadly. X-rays are better. Ultraviolet, with one exception, is pretty safe. But then why do you have to wear sunscreen when you go outside? Yeah, ultraviolet is divided into 3 bands, UVA, UVB, UVC. I don't remember which one, but it has a wavelength that's just exactly the right amount to destroy your skin cells. And so if you're exposed to the other ones, no biggie. But this one, you need to try to protect yourself. And so they make sure to put the right components into the sunscreen that's going to block that particular wavelength. And also in the atmosphere, there's a layer called the ozone layer. It takes in that one specific wavelength and it splits it into 2 other photons. So a photon comes down from the sun with a deadly wavelength, and there's something called Raman scattering where this one photon splits into 2, and those are safe now. So the ozone layer helps to protect us. If there's no ozone layer, you're not going to have that happen. So the ozone layer is a protective thing for us. Your microwave oven is very similar to radar. I don't know if any of y'all are old enough to remember when Amana first came out with its microwave ovens. What did they call them? It was the Amana radar range, because it's the same stuff as radar. I've heard that the way we realized microwaves could cook stuff is some guy at an Air Force base had a chocolate bar in his pocket and a radar dish swept by and the chocolate melted. So what happened here? It turns out radar microwaves are just the right amount of energy and frequency to get the water molecules vibrating and melt the stuff. I used to work at IBM, and we had the National Weather Service down on Loyola Avenue downtown, and one of the guys had a problem where right across the street, another government office, and at certain times the computers would just shut down. And he couldn't figure out what's going on. Why is this? So one day he was sitting up there trying to see what's happening, and just then he sees out of the corner of his eye a radar dish sweep by, and the computer shuts down. And so later on they realized, oh, it's not properly shielded from the microwaves. So you put aluminum foil around your computer and it won't be susceptible to the microwaves after that. Of course, one of my favorite bad science movies was The Core. Anybody ever see that? Okay, in it, the Earth's core stops rotating. Yeah, that's stupid. The Earth is rotating, the core is going to rotate. So anyway, the core stops rotating, and so the Earth's magnetic field is not there anymore to protect us from the deadly microwave radiation. It's not the microwaves, it's the ultraviolet. So if somebody puts their arm out of the car window and they get a bad burn from microwave. No, microwaves don't give you a burn like that. Ultraviolet does. Okay, and so X-ray machines take advantage of short wavelengths. These will go through your body. So we can use them for diagnostic purposes. And radioactive elements produce gamma rays. Actually, radioactivity is very useful in medical treatment. Besides the gamma rays, there's also something called an alpha particle that comes out of the nucleus of an atom. And when it does, it's basically a helium nucleus looking for a couple of electrons. So when it encounters anything, it's going to steal the electrons away from whatever it encounters, and if it's a living thing, it's going to kill it. So if somebody has a tumor inside their body and you're worried about beaming gamma radiation through, and it's still a localized tumor, you could inject some kind of an alpha emitter, some kind of an alpha particle source directly into the tumor, and it's going to kill the tumor from the inside out. Of course, it's useless once the cancer has spread, but it's a promising technology. Okay, so electromagnetic radiation, it travels as a wave, but it will travel through seemingly empty space. Waves seem to require some kind of a medium, but yet we've got this thing that's going through space that doesn't seem to need a medium. Well, that sounds like it's a particle. We call it a photon. Is light a wave or is it a particle? Yes. Is an electron a wave or is it a particle? Yes. Depends on the kind of experiment you're doing. It can act like a wave, it can act like a particle, depending on what you're doing. And the Bible says something about, well, okay, so electromagnetic radiation, depending on the experiment you do, it seems to travel in wave packets, it's waves, but the packet of waves is moving along as if it were a particle called a photon. And subatomic particles, protons, neutrons, electrons, they usually act like particles, especially when they're going through a wire in a DC circuit. But you also can diffract these things and refract these things. So this is behavior that we normally associate with a wave. So are they waves or particles? Yes. Back in 1924, there was a French physicist, a guy named Louis de Broglie. I left out his name, shame on me. He discovered that not only do electrons behave like waves, baseballs behave like waves, planets behave like waves, stars behave like waves. The wavelength depends upon the mass, but everything behaves like a wave under the right circumstances. So is matter a wave or a particle? Yes. The Bible long predated this. It said in Hebrews 11:3, through faith we understand that the worlds were framed by the word of God, so that things which are seen were not made of things which do appear. The visible things are made of invisible things. And I love the way Niels Bohr put this. He was one of the guys that really got the study of quantum mechanics going. And he said, if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. Everything we call real is made of things that cannot be regarded as real. Isn't that what the Bible said? I'm pretty sure Bohr was a Christian. He was a genius, and he got so many accolades. I think he got a Nobel Prize. But he was a cool guy, a Danish guy, Niels Bohr. So, waves are out there. Has anybody ever heard If a tree falls in the forest and there's no one there to hear it, is there sound? Of course, there's a variation on that. If a man speaks in a forest and there's no woman to hear it, is he still wrong? Okay. But what is sound? Sound is a vibration of air molecules, or it can go through water, it can go through solids, but typically we think of sound as going through air. If it has a short wavelength, that is a high frequency, it seems high pitched to us. But if you take a sound meter, you can say, okay, that's a frequency of 440 hertz. One person says that's a high frequency. Another one says it's a low frequency. Well, the frequency is an observable, measurable thing that you can use a measuring device and find out what it is. But then the pitch, that's a matter of interpretation. I think that's too high, that hurts my ears. Sounds okay to me. Likewise, loudness. There's a measurable quantity called amplitude. Loud, that depends on the distance between the compressions and rarefactions of the sound waves. So you've got a certain sound pressure level, and somebody hears it and says, man, that's loud. Somebody else says, what? That sounds okay to me. The sound pressure level is the same. It's our interpretation that's different. So if a tree falls in the forest and there's no one there to hear it, what happens to the air molecules? They still vibrate. There's still sound. That's really a Hindu question, which is based upon the idea that the observer determines reality. Oh, if there's no observer, there's no reality. Well, that's, from a Christian perspective, that's ridiculous. There's still going to be sound there no matter what, as long as they're vibrating air molecules. I'm trying to time this for 2 hours. Okay, there's something called the Doppler effect. Maybe you've heard of that before when you watch the TV program. They say, our Doppler radar shows this, shows that. The Doppler effect depends upon the fact that if you and a wave source are moving closer together, it's going to seem to be a higher frequency. If you're moving apart, it seems to be a lower frequency. It's stretched out. It was first described by an Austrian physicist named Christian Doppler. So if you're on a railroad train, you've probably seen this in the movies, you're coming up close to a crossing and the bell is there, and you hear it going ding, 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 and you get past ding, 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 ding. Well, the apparent shift in wavelength occurs because of the relative motion of the source and the observer toward each other or away from each other. Let me see if I can do this. I have to take the microphone off for this to work because it's going to be going around me. This is a constant frequency sound source. Now you and whoever's listening online, as I spin this around and it comes toward you, listen to how it sounds, and then it moves away from you, listen to how it sounds. Let's see if I could do this without hitting anybody or hitting myself. One time I was doing this in a physics class, and there was this one kid who never paid attention, never looked at me, and it accidentally, the string broke and it flew across the room and hit him, but fortunately it was in the back of the head and he had a lot of hair. He didn't even notice. I could have gotten in big trouble. Okay, so as it's coming toward you, can you hear a difference? Higher, lower, higher, lower, higher, lower, higher, lower. Okay, so in the microphone, I'm hoping that you're hearing that also. That's the Doppler effect. It works for sound, it also works for light. And we use this for several things. One of them is weather radar. You want to know, are the clouds coming at you or are they moving away from you? Not just how far away, but you see, here's the radar signal we're sending out, the microwave frequency. Oh, it's a little stretched out. The clouds are moving away. It's a little compressed. The clouds are moving toward us. Where did it go? So it's also used to determine how we're moving through the cosmic microwave background. I mentioned this, I think, last time. The Bible says that the sun is making a circuit through the heavens. And people scoff and they say, the sun doesn't orbit the earth. The Bible doesn't say it does. It's making a circuit through the heavens. There's a cosmic microwave background radiation field out there, and we can use the Doppler shift to determine, we're moving, the solar system is moving at about 1 million miles an hour through this microwave radiation field. So the Doppler shift tells us, the Bible was telling the truth about that. The sun is in a lengthy orbit throughout the Milky Way. I keep doing the wrong thing. Shame on me. Okay, so then another thing that we use the Doppler shift for is to try to determine our relative motion as compared to the stars out in space. And we're going to get into this another time later on. A star puts out a certain color of light. The wavelength gives us the impression of this is what the color is. So if that's the actual wavelength of a star's light, we're going to get into the chemistry part later on. Whatever elements are between us and the star, they emit certain colors of light, or depending where they are, they may absorb colors of light. So the outer edge of the star is going to absorb certain colors of light, so you can look at what the pattern is of the colors and determine, what elements are in that star. Well, this is an extremely exaggerated view there. The wavelength may seem to be stretched out, and it's because there's motion between the Earth and the star. Who's moving, the Earth or the star? Compared to what? You know what I'm about to do? I'm about to move this building. Who's moving, me or the building? Compared to what? There's a really stupid question people ask. Could God make a rock so big he couldn't move it? They don't understand what motion is. It's compared to what? All he's got to do is move away and he moved it. Okay, so if we see the wavelength of that light from the star seem to be stretched out, we say, we're moving away from the star, or the star is moving away from us. And if it seems to be compressed, it's called a blue shift, toward the blue end of the spectrum. We say we're moving toward it, or it's moving toward us. So this is how scientists, I don't know if you'd say scientists, but this is how evolutionists determine how far away the stars are. Last week when we were talking about the astronomy stuff, I pointed out that using parallax, we can only tell the distance to stars up to maybe 50 light years away, but yet you'll hear that this thing is 2 billion light years away. How do we determine that? It's by analyzing the color of light, and we say it's moving away from us this fast. The Doppler shift is the standard interpretation, but it's not necessarily right. If there's some other thing that's causing this shift toward the red or the blue end of the spectrum, then all bets are off as regards to the size of the universe. That would probably be a good place to stop because we're getting into pendula or pendulums. Okay, so I think we'll stop now. It's been just under 2 hours for those that are watching the video. Let me know if there's any problem with the sound. I hope it works, Lord, please let it work. And for my audience that came here to help me out, thank you very much. Okay, that's it for the night. To help me out, thank you very much. Okay, that's it for the night.